today's lab also, like some of the students, some of the groups will be having Viva, and I guess Akanksha is in the process of sending emails for the particular groups who have to show up. So she's sending you the time, exact time when you need to come. I mean, so whichever group has been scheduled, they'll be informed separately. So last time I saw that some groups didn't show up for the Viva. So this is not acceptable. So because if you don't show up for the Viva, it's as good as not submitting the assignment. So we take it very seriously. So when you're called for a Viva, please show up. Okay. All right. So yeah. So let me just share my screen. I think it's not shared right. Yeah. Okay. So yeah, I hope the screen is visible, right? You're able to see the screen? Yes.
Yes.
Okay. So cool. Cool. So coming back to reinforcement learning, so that's where what we were doing this week. Somebody said something. Okay. Okay. Fine. I guess it was a mistake or something. So, okay, so we were looking at reinforcement learning, where it was an extension of an MDP, a Markov decision process, where the transition probability, so the probability of reaching a destination state, given a state S and A, that you took the action A. So this there was a probability, there was an underlying randomness there, but this probability was not known to you. And the reward function, so the reward, the one-time reward of going from S, taking an action A and going to S dash. So this kind of a reward that was also not known to you. Okay, and all that was known to you was the set of states, and there are these actions, and if you do some action you will see some reward, but you don't know beforehand these parameters. Okay, and then we were trying to see, like, how will you learn a policy, or how are you going to learn the values of the states. The different problems here. So what we started off first was, if you had some data, some information, so these were called episodes. Okay, where you start from some state and keep doing some actions till you reach the terminal. And we said that if you are given these episodes, one possibility is to learn these transition probabilities and the rewards. So this is just by using a frequentist estimate. So number of times some event happened divided by the total number of events. So this is also called a maximum likelihood estimate. Okay, so maximum likelihood. So you will see these things a little more in detail in your machine learning course, and maybe, that's in the next sem, and maybe also if you're doing an optimization course you will see some of these details. But so this is like these kind of estimates are called maximum likelihood estimates. And so what this method was to learn the transition probabilities and the reward function explicitly, and then use whatever you know in MDPs. Use these as the transition probabilities and use value iteration or policy iteration schemes. Okay, so this was called model based learning, where you explicitly learned these parameters. Okay, and then yesterday what we did was we tried to go into a slightly different approach, which was called model free learning, where you don't in particular you don't learn these parameters, you don't explicitly learn the parameters, but what you do is, you based on the samples that you get, you do some operations directly with the samples, so that it gives you what you need. Okay, so in this context, what we first started off was, if you have a fixed policy, somebody told you that for these states you need to take these actions. Now under this, can you estimate vpi, the value of each of the states under this policy? Okay, and here the first method we saw was called direct evaluation, where you take each of these episodes and you see how much you earned in the process. So starting from B, what was the total value you got in the sample, and you do it from each of these samples, and then you take the average. Okay, so this is also called Russell Norway calls it direct evaluation, but more generally this is called Monte Carlo sampling. So have you seen Monte Carlo sampling in your probability class? Did you see something like this? Okay, am I audible?
Yes, ma'am.
Yeah, okay. So, did you see Monte Carlo simulations or sampling in your probability class? It's yes or no or unsure what?
Ma'am, just got an idea from probability theory course.
Okay, okay. Yeah, so you probably saw like if you had some samples, how you estimate something, right? So this is exactly the same thing. You draw some samples of the quantity you need. So in this case, it's we are trying to estimate the value, and you directly take the samples of this value, and then do an average. So that's what this was. Okay, yeah. So then we saw that okay, can we do something better than this? Okay, so we saw an intermediate method where we don't take the entire value of the sample. For instance, for the value of b, we don't take minus 1 plus gamma times minus 1 plus gamma square 10. Instead of doing that, what you do is you make use of the value you've already learnt of the state c. Okay, so that's what the second method was, and this was kind of building on policy evaluation that we saw in MDPs. When we learned MDPs, we saw that if you know all the probabilities and rewards, and you want to estimate a policy, the values of the states under a policy, there is this update you can use. You can do this in an iterative manner, and yeah, so that was a computation we saw. So if in this case we don't have the probabilities or the rewards, so what we said is maybe use the samples in these updates. Okay, but there we saw that if you do, I mean, if you just start off doing this method, like you start off with v0 as the value of the status, when you have 0 time steps left. Okay, you take that as 0, and in the next time step you want to get several samples of what happened when you started at s. So there is this issue that if you start with s, you took this action pi s, then you would go to s dash. Okay, and now if you want one more sample of s, I mean, if you want one more sample of what happened at s, you have to come back to s, or you have to wait for the next episode. Okay, after all the transitions are over, then you have to again come back and see, right? So that was the kind of drawback in this method. So this method is just something that I just wanted to bring this idea in of using samples as well as this update. Okay, so you probably may not see this in a lot of textbooks because it's not a very standard thing, uh, but the UC Berkeley course calls this method as sample based policy evaluation. Okay, so I mean, it's just a very loose kind of a method. Okay, sample based policy evaluation. So even the guarantees and all that, we don't know about this method. So the thing is that since it's trying to simulate policy evaluation that we did, so you expect that after a lot of iterations, after several values of k, and if you have a lot of samples, then you expect this to kind of converge. So this is something that you can also try to implement yourself. Try to generate some samples, like keep any of the MDPs we saw, right? We saw the racing car MDP. So keep the probabilities as what we used, but try to generate samples. So then finally, when you apply this method, don't use the probabilities that were fixed. Generate samples. So in Python, you have the this and this multinomial samples, right? So in NumPy, you have this kind of function where you can draw multinomial samples. Okay, so try to do that, and then see what happens, what this approach gives you. Okay, so this is just a homework for you. Try these both methods. So what I want to do today is like I want to build on this method. It's a variant of it to handle the drawback that as and when you see samples, you cannot make use of it in this approach. right? You have to see the samples, and then you have to do these iterative updates, because for each update you make, you need multiple samples, and so you're not able to do this. So how can we overcome this drawback? Okay, so that's going to be the next approach. So let me start a new page. Yeah. So this is today. It's one of the standard approaches for evaluating a policy, for learning the value of a policy. So it's called temporal difference learning. Okay. Um, okay. So before I specifically talk of the this example in RL, the value of each of the states, let's just take a simpler example where there's a random variable x. Okay, so this is a random variable, or let's just take the height example. Okay, so yesterday we were seeing that I wanted to estimate the height. What is the average height of all the students? Okay, I mean all third year engineering students, and what I have is your class. Okay, so h is the random variable, the height of the students, and what I have. So this is the random variable, and I have h1, h2 like that, up to some say hs. Okay, let me just call it h yeah hl. Okay, so as many as this is the length of this vector, the number of samples I have. And we saw that one way is you just take the sum of his by l. Okay, and this can be one estimate. So this is an estimate for the expected value of the height. Okay. So this is what we saw yesterday. And of course, there is this other way in which you compute the probabilities of each of the heights. Okay, and then taking to and explicitly compute it using the formula. But we'll focus on this kind of approach because we were looking at model free learning. Okay, so these are all samples. Okay, so yeah, if I had to do this estimate, as and when I see the first sample, I say, this is my estimate. Now, when I see the second sample, I revise my estimate. I want to do something like that. Okay, so what I could do is I can have something like this. I have S is my estimate of the, okay, let me just call it maybe h star itself, or h hat. So this is my current estimate. Okay, this is the current estimate of the mean. Okay, and I'm going to keep updating this. Okay, so what I will do is if I have the current, so I've seen samples like h1 to hn, and based on this I have an estimate h hat. Okay, and now I'm going to see a new sample hn plus 1. Okay, so this h hat is whatever I have here is just hi by n. Okay, now when I bring in hn plus 1, how will I update my new mean? Right, can I update the new value of h hat using this old, let me just call this h old. Okay, I want to basically compute h new in terms of h old and hn plus 1. Right, so do you know how we can do that?
N times h old plus hn upon n plus 1.
So n times h old, yes, plus
The current sample that you got.
current sample, and it's an average, right? So this whole thing by n plus 1, right? So I hope this is clear, right? So if you just substitute it, n times h old is going to give you sum of hi. Okay, and then you're adding in hn plus 1. So actually this n is not here, right? It should be, yeah, n times h whole plus hn plus 1 divided by n plus 1. So this will give you, this is just going to exactly give you hi by n plus 1. So I is 1 to n plus 1. Okay, so yeah, this is kind of the idea in temporal difference learning. But one thing here is that, okay, let's just write it in a slightly different way. I can write this as h old times 1 minus alpha plus alpha times hn plus 1. Okay, where alpha is n by n plus 1, right? Or alpha is 1 by n plus 1 rather. Alpha should be 1 by n plus 1. Okay, I can do this, right? It's just the same thing. I've substituted alpha as 1 by n plus 1. And, so I've just written it in terms of alpha h old and hn plus 1, right? So this is something I can do. This is a valid way to update it, right? Is this clear to you all? Right, I want some response at this point. Yes, Advait,
Yes,
it's
ma'am.
clear?
Yes, ma'am.
Yes. Okay. Okay, so now what I want to tell you is, okay, so this is a very specific value. We took alpha as 1 by n plus 1. So it turns out that, this is not very crucial. If you have enough samples, any value of alpha, any small value of alpha you have here will work. Any small value of alpha, okay, will work. Okay, this will work. Okay, so something like alpha around 0.1 or 0.01. Okay, it depends on the the number of samples that you have also. But generally, a small value of alpha, if you keep, that's going to work. Okay, so why do you want a small value of alpha? It's because you don't want any one sample to dominate. Okay, so I remember alpha is the weight for the new sample. Okay, and that's what this would mean, right? And so if you give a large value of alpha, then one particular sample can dominate over others. So you don't want that to happen. And so over time, if you have a small value of alpha, it does well. Of course, if you set alpha equal to 1 by n plus 1, so alpha at each step end, right? So at the nth step, if you set it as 1 by n plus 1, so that alpha diminishes over time, then it's even better, right? You will almost exactly get the value of the sample mean. Okay, so maybe let me just show this to you with a small snippet. Okay, so what I have here is a code where okay, let me just comment this out. So what I've done is, I've just drawn samples from a normal distribution. Okay, so it has a mean of 5. Okay, so I'm just going to draw a few samples. So I'm just starting off with 10 samples. Okay, and what I'm doing is my initial estimate is very bad. So S is my initial estimate of the mean. So that is 30. And I'm just going to do this update. So 1 minus alpha times S plus alpha times the new sample. Okay, and at the end, I'm going to see what the value is. Okay, so is this code visible?
Yes,
Yes.
sir.
Yes.
Yes.
Okay. Okay. So let's just run this. Um, okay. So you see that these are the samples. It's printing the samples. Printing the estimate. Okay. So S is the estimate at each point of time. So it's printing these estimates. So you see that we started off with a very bad value, 30, and I have only 10 samples. So it's coming closer and closer to 5, and after 10 samples, the value is still bad. It's about 30. Okay. Now, if I increase my number of samples, and I've fixed alpha as 0.1 here, if I increase the number of samples, it's better. It works. Okay. Right. So these were all the estimates. The estimates started off bad, like 27, 25, like that. And after 100 samples, it's kind of close. Okay, now let's just keep 10 and a value of alpha as 0.01. Okay, so here this is a case where a small value of alpha is not helpful because my initial estimate itself is very bad. So I will need a lot of samples to bring it close to the true value, right? So about 1,000 samples and now it's close. Okay, but generally you will start with maybe something a little more meaningful, the value of S. And note that, even irrespective of whatever value of alpha I've put, right? If I have enough number of samples, it's going to converge. It's not that alpha has to be, 1 by n plus 1. Now, if I put alpha as 1 by I plus 1, so initially alpha is 1. So I'm entirely going to estimate based on my first sample. And as I go along, the next step alpha is half. Then it's 1/3 like that. Okay. And if I do that, maybe let's just keep 10 samples and see what happens now. So yeah, in the alpha, it's going to take this update. So you see, it's actually quite good. Alpha is 1/n is actually a good estimate to have, right? Because right from the first sample, you're taking it seriously. And, of course, because you have only 10 samples, it's now 5.8. But let's say something like this, it's better. It gets better and better with time. Okay, so the idea of showing you this was to see that this value of alpha, it's not necessary to be always 1/n+1. Sometimes even constant alpha parameter works. Okay, um, but it's yeah. So that's the idea here. Okay, so a full proof of why this converges, it makes use of ideas of stochastic approximation. So we are not going into that here. Even like a full-fledged RL course wouldn't deal with it. So this is something that you have to understand, that even small values of alpha, if you put, it works. Now if you actually put like large values, say something like let's say 0.6 or something, that's not going to work, you see. So that's like very sensitive to the samples. So you see, the last value was 3.6, the previous value is 4.2, but it jumped very drastically because the last sample was possibly quite bad, and that's why there was a jump of this kind. Okay, so typically, if you fix like small values of alpha, this kind of an update works. Okay, and yeah, so the idea in temporal difference learning is just to use this way to estimate your average, I mean, to estimate your mean. Okay, so I just told you the simple example so that you see this update. So now let's look at applying this to the case of MDPs and RL. Okay, so remember what we had was we wanted to estimate the value of a state S under a policy pi. And what we had was, so now we're trying to do it in an online fashion. Online in the sense that you are going to see, so what's going to happen, you're going to see a transition from state S, you're going to see some action, and you're going to land up in state S dash, and you will see this reward. Okay, so this is what you will observe. Okay, and of course here the action that is taken is exactly what the policy gives you. So this is pi S, right? And so what you're going to do is, now you have a new sample for what happened when you started from S. So what you will do is you'll keep some estimates. So what you will have is V of S for every state. So this is the current estimate. Okay, so this, you have this vector. I'm just writing it as V of S, okay, without a pi and all that, so that the notation doesn't become too cluttered. Okay, so the current estimate, if I'm calling it as Vs, now after this, what is going to happen is I'm going to observe this sample. Okay, so observe this sample, and after this, what I'm going to do is I'm going to do some update to V of S. So particularly the update I'm going to do is 1 minus alpha times my old estimate. Okay, so 1 minus alpha times the old estimate. So this is the old estimate, plus alpha times the what I got from the sample. Okay, so now the sample, I have to see what to fix here. Okay, so the new sample, the value I'm going to take is going to be this reward from the, this is like a one step reward. So I start at A, take an action, I mean, start at S, take an action A, go to, some intermediate state, and yeah, finally S dash is what happened. This gave me a reward R. And this is also the state S dash would have, my previous estimate was that this is of value V of S dash, right? So the sample is actually going to be R plus V of S dash. Okay. And so what I'm going to do is I'm just going to say, use this value v of s dash, where this is old estimate of s dash. Old estimate. Let me just write it
And
properly.
shouldn't we have a discount factor?
Yeah, correct. Thanks for reminding. So this is gamma times vs dash, right? So r plus gamma times the old estimate for value of s dash. Okay. So the reason why I can do this is, remember that for v of s, the value of a state s, in terms of ultimately where did it come from? It came from this equation, right? So the summation of the transition probabilities and r plus gamma times vk. Okay, so this is where it came from, and this in turn was an expectation, right? So this was the expected value of the one-time reward plus gamma times vk. And so because we are trying to again estimate an expected value here, so that's why we are trying to use these ideas of averaging. And so that's why this method works. Okay, so the overall algorithm will be like this. You have you start off with v0. So let me just write the algorithm once so that it's like really clear. So overall algorithm is v of s is 0 for every s. Okay, and so now the input is also a policy, right? So input is a policy pi. Okay, so pi is like for each state you know what action to take. Now you decide how many episodes you're going to do. So for each episode that you do, so for each episode, what you do is you're going to do a transition. So the current state is, so there's a current state. So current state is maybe some s. Okay, so what you're going to do is you will start off with, the action is pi of s. Okay, and you observe, uh, what you'll observe is s a, uh, sorry, not s a, and s dash. So it actually went to s dash and you got this reward. Now what you will do is you will update v of s is 1 minus alpha times your current estimate plus alpha times r plus gamma. So this is the reward r plus gamma times v of s dash. Okay, you will update this, and now your new state is so new state is s dash. So new state, let me just say it s, is s dash, and you'll keep looping. So do till you reach a terminal. You reach a terminal, or if there is no terminal state, you do it up to some time steps. Okay, so you keep on doing this, and after one episode, again what you have is you have the current values of all the states that you learned up to this episode. Now the next episode starts with this new value, I mean this value of vs that you have got till this point. Okay, and you keep on doing this till all your episodes are complete. Okay, and at the end you have the value. Okay, so here what I've told you is, I've also shown you a process of how you can generate your data. Okay, because your goal is to evaluate an input policy pi. So what you're doing is you are going to take this action and you'll simulate this. So this is actually a simulation step where you will simulate s and a, and you will see what happens. S dash and r is what you get, and then you will update your value. Okay, is this idea clear to you all? Any confusions, any doubts? Okay, Aditya, Advait, they're clear. Uh, okay, okay. So I just want to ask, what about Gunjan? Not been hearing from Gunjan in some time.
Yes, ma'am, it's clear.
It's clear? Okay. Uh, what about the others? Meet Patel?
Yes, ma'am. Clear, ma'am.
It's clear? Okay. All right. Yeah. Okay. So I thought maybe I can just show you this with an example, with the same example, right? So maybe let me just use the example from the Berkeley site, the site itself. So maybe we can just go over this example. Okay. So let me just use this. Okay. Okay. Fine. Let this be. Okay. This is okay. I'll take the whole of it so that. Okay. So, okay, they've told the values here as well, but what I want you to focus on is this part of the grid. Okay. And what is going to happen here is like now I'm given this transition. So, this is the state B. Okay. So, B, C, D, and A, E. So the current values are what is given here. So 0008. So value of state D somehow, this is an intermediate step of temporal difference learning. And the value has been estimated to be 8. Okay. And now I see this transition B east C minus 2. Okay. So I took a transition from B, I went to C and I got a reward of minus 2. Okay. And now I'm trying to do this update. Okay, so let's use a different value of alpha because half is what you see here. So maybe let's use alpha equals 1/4. Okay. So yeah, so can you tell me what are we going to update now once we see this sample? So what we have seen is B. uh, so we took an action east, you went to C and you saw minus 2. Okay, so can you tell me how I'm going to do the update now?
3 by
So
4
what should I,
B.
pardon?
3 by 4 times V of B plus 1 by 4 times minus 2 into gamma
Yeah,
time V of C.
yes. So 3 by 4 times V of B, right? So this is what I'm updating is V of B, and this is 3/4 V of B, the current estimate, plus 1/4 times the reward that I see now. So that reward was minus 2 plus gamma times V of C. Okay. So in my current estimate, V of C was 0. So this value is 0. So, and what was value of B?
0.
This was also 0. So what I am going to get is minus half, right? Minus, yeah, so minus half. So accordingly, this values get updated now. So what you're going to have is 0, minus 0.5, 0, 8, and 0. Okay, so this is my new set of values. Okay, right? So now I see one transition C east D minus 2. So C east D minus 2. This is what I observed. Okay, so let's just do this one update. So now what's going to happen? So this is B, this is C, this is D, and A, E. So maybe let me ask somebody this time. So Advait has answered. So, okay, Sejal. So Sejal, you're there?
Yes, ma'am.
Yeah, so can you tell me what the update is going to be now once I see this transition? Which value should I update? Okay, Sejal has become quiet. Sejal, is this clear? The update, this temporal difference learning algorithm, do you understand it?
Hello.
Yeah, Sejal, yes.
Yes, ma'am. Can you repeat?
Yeah. So what I'm asking is, I think you got disconnected or something. So,
Yes,
uh,
ma'am.
yeah. So we did this iteration, right? We got the values of all the states. Now from C, I'm taking an east, and I'm taking an east action and going to D, and I see a reward of -2. So can you tell
Yes.
me what the update is going to be?
V of C.
Yes, V of C. V of C. What should
Uh,
I change it to?
uh, just a second. 3/4.
So three
Uh,
by four is because I'm just asking you so that if something is unclear, it will come out, and we can discuss it further. Okay, I'm not trying to torment you or anything. Okay. Yeah. Sejal, go ahead.
uh, Here asking me why we need to have it 3/4 here
Yeah. How are you getting the 3/4?
by 1 minus alpha in the formula above.
Yes. Okay. So 1 minus alpha. So this is 3/4 times.
Uh, V of C
Yes.
plus 1
Plus.
by 4
Yes. Times something, right?
uh, e, yes re- uh, minus 2 plus
Correct.
gamma of V of D.
B of t. Right. Okay, so this is the update. Good, Sejal. So so let's say I'm taking gamma as 1 itself. Okay, so what will these values be again? So 3/4 times what? So can you just substitute the values? Maybe let me ask somebody else now. Okay, Twisha.
Yes, ma'am. Yes, ma'am.
Yeah. So can you substitute these values and just tell me? So what's the value of V of C currently?
0.
0, right? So what we are doing is we are looking at this table. So this is the set of values, right? Current values. Okay, so 3/4 times 0 plus 1/4 times -2 plus, what's it going to be?
1 into 8.
8. Okay, good. So this is going to be, so you're going to get 6/4. Okay, so this is going to be 1.5. Okay, so this is how the values get updated. So value of C was 0, and it with the sample it got updated to 1.5. So this keeps going on till you've seen all the till all after all the samples are seen, you get the value of pi. And so this actually, this method, this temporal difference learning, this was a major idea in RL, and there have been like convergence guarantees for temporal difference learning, but the condition is that alpha has to be small. Okay, so maybe even this value 1/4 is something we just took it for now, but typically the values are really small, like alpha is typically like zero point 0.1 or 0.01, something like that. Okay, so for under some conditions of alpha being like quite small, temporal difference learning has good convergence guarantees. Okay, that's the result. And so one thing is, why is this called temporal difference learning, right? So the reason is that when you see this update here, what happens is I can write this update in a slightly different way. So this update is actually, if I take the VS terms first. So what I can do is I can say this is VS plus alpha times, this is the new reward, right? New sample. So I'm just writing it as new sample so that it's clear. So this R plus gamma VS dash, that's the new sample, minus VS, right? So it's the same update that I've written. So these two are actually equivalent. Okay. So here you see that there is an alpha parameter and there is this difference here. So this is like, how much your new sample contributes to VS, and that difference is what contributes to the learning. So that's why this is called temporal difference learning. And temporal because, over time, as and when you see your samples, there is an update here. Okay. And this parameter alpha is also called the learning rate. Okay, that decides like how fast you learn things. And of course, you can't keep it large, as we have already seen. Okay. Yeah. So this kind of updates is actually very popular in a lot of streams, like in machine learning. Several algorithms you see will use this kind of an update. Okay. And more generally, this sort of update will come in optimization. Like it's what is referred to as gradient descent, and that's where typically this generalizes to. Okay, so I don't know in the next semester whether I'll be teaching optimization, but if I do teach optimization and if you are taking that as an elective, you'll see the foundations for why this kind of updates arise. Okay, all right. So is this notion clear? Is this algorithm clear to you? Temporal difference learning. I want a show of hands or show of or just type whether it's clear. Yes. Okay. All right. So, okay, cool. So the next idea is, so you see like, okay, so far what we did is we looked at how you can evaluate a policy or how you can learn the value of a policy. So learning the value of a policy, in fact, all these methods that we had here were aimed at learning the value of a policy, of a given policy pi. Okay. And temporal difference learning, this made use of, it was a combination of ideas. So one was this Monte Carlo estimate, that kind of idea, like direct evaluation. There were some concepts from there, but you also tried to use some ideas from dynamic programming by saving the values of V and trying. Okay. So it was like a combination of dynamic programs and sampling. Okay. And so this is good if you want to evaluate a policy or learn the value of a policy. But remember, what we wanted to do was to learn the value of the optimal policy. Okay, so right, and the optimal policy is something you don't know beforehand. So if you already knew the optimal policy, there's nothing. I mean, you just tried to learn. If you wanted to just learn the values, then you could do this. Okay. Is there a question? Suryansh, you have a question? Suryansh?
Yes, ma'am.
Yeah, you have a question? I mean,
No, ma'am.
okay, fine. All right. So, what we are now trying to get into is how do you find the optimal policy, right? Um, to find out the optimal policy, you need the best values V star in some sense, and to know V star, maybe you need the optimal policy, right? Like if you knew what exactly the optimal policy was, maybe you could compute the V's, you could learn the values of V's, but you don't know the values of V's, you don't know the transition probabilities, you don't know the rewards. So how now can you find the optimal policy? Okay, so this is like one step. We are again adding one more step here to the temporal difference learning idea. So suppose you had the data that was given. So the data in the form of episodes was already given, right? And so you had these, something like these transitions, or even whatever we saw earlier, the couple of such episodes if you had, right? All these methods are telling you how to find V pi. So is it possible to tell the best action if you knew V pi? Or if you know the values of the states, is there some way you can tell the action now? What's the best action to take in each state? Do you think that's possible? Let's look at temporal difference. That's the best known algorithm, right? So with this algorithm, at the end of it, what you're going to get is, v of state 1, v of s2, all this is the output. Okay, so if there are s states, these are you're going to get. So is it possible to tell what's the best action now at each state?
No.
Not possible, right? So you need something better. Okay, and that is what is going to bring us to this concept of Q learning. So the idea is, remember our V star, right? So what did it do? You started with S, you tried to take some action, and you reached a Q state. And here, one state, some S dash would occur. So if you took action 1, you'll have one particular Q state. Now, if you took action 2, you're going to get some other state. And here again, you have a set of other states. S is maybe double prime. Okay, so given this, what you wanted at S was the Bellman equations told you that you wanted max, the best action that gave the expected value of the one-time reward R S A S prime. So this is an expectation over S dash plus gamma times V star S dash. Okay. So the issue is like you need to get this max over all possible actions. Okay, and remember, like with samples, what you can estimate is an expectation, but if you have a max, this is something that sampling doesn't really tell you what to do. Okay, so what do you do now? So the big idea is that so this quantity is what we refer to as QSA, Q star of SA. If you remember, this is what we said, like this is a Q value of a value of a Q state. Okay, the optimal value of a Q state. Okay, so instead of trying to update your values, what you can do is just try to update your Q values. Okay, so instead of doing all this learning on the values of states, instead, whenever you see a sample, what you do is you try to say that Q star is this. You try to do the same updates. Okay, so let's just write what it comes down to. So maybe initially you start off with Q star, so let's just call it Q, okay? So Q of SA is 0 for every state action pair. Suppose you start off like this. And then what you do is when you see a sample, so you see a sample SA, S dash R, what you do is you say that QSA, so what you're trying to approximate is this one. Okay, and so this is just 1 minus alpha times your previous Q value plus alpha times some sample, right? So here you can use the reward that you got plus gamma times V star. Okay, so now V star, there's an issue because you're not computing V stars anymore. You're computing everything in terms of Qs. Okay, uh, right? So that's a subtle issue, but there's something more you can use if you try to understand what V star actually is. Okay, so I'm running out of time, so maybe I'll just take about 2-3 minutes more and I'll let you go. So V star, actually, if you see what V star is, if it's again a max, right? So V star of S dash is again a max over a set of other actions, the same expectation, right? Expectation of maybe some other states, okay, and the same quantity. Okay, so what you could do is, so this is again a max of, if you take Q S dash and A dash, right? So what you can do is you can just use, and Q S dash A dash is something that you already have. Okay, you're saving this. So what you can just do is use those values. Okay, and keep doing this. Every time you see some action, some transitions, keep doing this for all your episodes, and then you learn cues. And finally, what you do is, at each state, at the end, what you say is, the max of QSA, Q of SA at every state. So this is going to be, so argmax. So argmax, the action which maximizes this is going to be your policy. Okay, so that's how you can learn, the optimal value. So this converges to the optimal value. okay, if you have enough samples. So anyway, I just went very quickly over this. So this is actually called Q learning. Okay, so what I will do is maybe we'll just have one class on Tuesday. So I'll just spend some time on Q learning because this was a bit hurried. So I will spend some time on this and also tell you how to generate your data. So what I said here is if you have the data, how you estimate the optimal policy, but how do you actually generate the data also? This is something I'll do on Tuesday. Okay, so I'll stop here for now, and maybe if there are any questions, I'll hang back. Otherwise, thanks everyone.